Here we're going to look at generating censored exponential data with a specific proportion of censored data in mind. So if you want 20% censored, or 10 or 80 or 50 or anything like that, that's what we're going to cover today. At least one approach to generating that data. Now we're going to go through a little bit of theory, and then we're going to do an R illustration, and it's very simple, very straightforward. So if you want to skip the next 2 or 3 minutes, you're welcome to. But here we're going to let the failure times be exponential with some lambda 1 parameter, and the censoring mechanism is we're going to make exponential also with some lambda 2. And in general, we observe the minimum of these two. And this is the data that we observe in experiments in real life. And then we carry around these ordered tuples, these pairs. This is the minimum of the failure time or the censoring time. And then we also have an indicator of whether it was censored or not. And that's what this is. So here, this is the whether it's censored or not, and the probability that it's censored is just the probability that C is less than X, and we can set that to some known P and then back solve for the lambda 2 parameter to find a specific proportion P. So the steps are very simple. Is we choose our failure rate, our lambda 1 parameter for our failure times. What proportion do we want to be censored? And then we back solve for lambda 2. And this ends up being a very, very simple solution. But here's how you go about solving it. So we want to know, we want to find the probability that C is less than X. So if this is our graph of C and X, and this is the C equals X line, we want it to be down here. So the probability is this. We want to integrate the joint density of X and C over this region. But X and C are independent, so we can split them up. And then now we start integrating. So we take the f of x outside of the C integral, and this is the density for C. And we integrate it, and we get this. Our limits of integration are 0 to x, and we get this. Now we multiply this into each of those, and we get this. Well, the integral of a density over its domain is 1, and now we integrate this in regards to x. So here is the one piece, and then we combine the exponents, and we integrate this, and it comes out to this. Here's our limits of integration, and this ends up being this. Multiply that in. So this is the probability that C is less than X. So we set it to some known P, to like 0.1 or 0.4 or some percent, and then we solve. So we subtract that to this side and add that to this side, we get this. Then we multiply this piece up and then multiply the 1 minus P in, and we get this. And then when we subtract some of that over, we get a reduction on this side. That's algebra, I'll let you do it. And then to solve for lambda 2, we divide both sides by 1 minus P. So this is the formula. So if we set our our failure time lambda parameter, then the censoring mechanism is just P divided by 1 minus P times the lambda parameter for our failures, and then that generates the specific proportion of censored data that we're after. And now let's do a quick illustration in R. Okay, here we're in R. I'm on a Ubuntu machine, and we're going to generate censored exponential data. And here, the sends rate, I'm going to let it be about 20%. We're going to do this for a sample size of 500. Our lambda 1 parameter for the exponential distribution is 0.02. And we're going to do a little simulation of what the proportion is each time. We're going to do this 1,000 times and collect them in this vector called prop sens, which is the proportion of censoring at each rep. We're going to rep this 1,000 times. Here x1 is our failure times, c1 is our censoring mechanism, and here it is. So we're using L1 times censor rate divided by 1 minus censor rate, and we want the minimum of those, so that's our Y1. And this, we're going to collect the proportion that have been censored and stored in this vector, and each loop is going to store the results in the next component of that vector. And let's just do a little histogram, and notice that the censor rate we wanted was 20%, and this is centered around 20%, which is what we would expect. So let's center and let's shoot for a censor rate of 50% and rerun, and it's centered around 50%, which is nice, and that's what we would expect. Now let's generate this for 2 samples, and here CR1, that's the censor rate for population sample 1 is 10%, sample rate for population 2 is 30%. This is L1 and L2 are lambda parameters for the failure times of our 2 populations. Sample sizes in each is 175, and then we're going to create this is sample 1 is just a vector of 1s to indicate we're at sample 1, and this is going to be a vector of 2s that indicate we're in the second population, because we're going to combine those. We're going to do some graphs and a little log rank test. So here we generate the data as we did before. Here is the sample 1 failure times, the sample 1 censoring times, and notice it's the CR1 divided by 1 minus CR, and then we use the same lambda parameter. We want the minimum. We need to create an event variable. Here this is the failure times for the second population. Here's the censoring mechanism. We take the minimum, create an event variable, indicator variable for event. Now we're just going to combine sample 1 and sample 2 into one long vector, and the same thing with the events, indicators, and the sample. So now when we plot this, we need to load the survival, and then here is the Kaplan-Meier curves for each of the 2, and then the serve diff with rho equals 0 is the log rank test, and the p-value is 0.07, not quite enough evidence to suggest they're different. And I'm going to rerun this, but reduce the amount of censoring. Let's say it's 15% in this one and 10% in sample 1, and rerun it under identical scenarios. And here's the Kaplan-Meier curves, and this p-value is 0.8, which that's a little surprising to me. I'm going to rerun it and see what happens. It's 0.1 this time, so not much evidence. But anyway, that's how you generate censored exponential data with a specific proportion of censored observations in mind. Hope you enjoyed the video. Like it and subscribe so you don't miss the next one. Thanks. Bye.